Okay, let's look at these questions. So here's our key. Momentum is defined as, and this was taken directly from one of my slides. So what was momentum defined as? Inertia in motion. It's telling us about something's desire to stay in motion.
Question number 1.
Okay. Don't publicize. Oh, Brittany. Oh, that's a shame. Not that she got it right. That's not it. She put "Go Patriots" on her paper. I didn't. Okay, number 2. Which of the following activities is doing mechanical work? What does mechanical work mean?
Force over a distance.
Force over a distance in the same direction or opposite direction for negative work. So the force has to be the same direction it's moving. So which one of these has a force and motion in the same direction?
B.
You know, this one here I'm going to have to cross out.
It was supposed to be like
It was supposed to be not. I missed that word. So I told you I'm going to throw it out, right? That's why you were working on it. Go ahead.
But if we put
I'm not going to grade it because then I have to be, trusting. Oh, yeah, she knew I made a mistake. And so she said, using his mistake, I can't do that. And likewise, if you answered anything but D, well, that would be consistent with the question. And as Brittany was, perplexed, what I do when I take this is I always take the first one and forget to read the rest. Like usually there's all of the above and I just miss it. So pushing your sister down the slide. You're pushing. Is she moving the direction you're pushing? By the way, the student who wrote this just said pushing down your sister. I wanted to make this a little more friendly. I'm pushing my sister down the slide. Something that's good. Bench pressing a barbell. You're putting a force. It's moving the direction you're pushing, hopefully. Pulling your sister on a wagon. Pull, that's a different kind of force, but it's still a force. And the wagon, assuming that the wagon is moving with you, that you're not being a mean brother and saying, oh, I'm pulling, but I can't go anywhere. Yeah, that's good. I said a brother because that's what I would be. You could be a sister. Pushing against the wall was the one that could not be work because what? It's not moving. And then throwing a ball. It moves direction. So this one here, the answer was supposed to be pushing against the wall, but it was supposed to have that word not. And so I will not count it in the grading. Brittany.
So the mechanical work is when your force and distance is in the same direction.
It's a positive mechanical work if they're the same direction. It's a negative mechanical work if they're opposite directions. And it's no mechanical work if they're perpendicular.
So what are the 2 different ones again? Or is it 2 or the one?
Well, mechanical work is the only one we talk about in physics. But I just put in mechanical there so people wouldn't say, remember I talked about in class, you have the energy being consumed by your body to push on the wall, right? So there's energy being consumed. That would be a work, but it's not a mechanical work. It's not a force and relaying distance. Okay, what is an apt depiction of potential energy? What is potential energy? Energy that's stored, energy because of its position. So which one of these? Okay, a stretch rubber band. You stretched it. If you let go, it's going to snap back because you stored energy. A ball rolling across the floor. What kind of energy is that showing? Kinetic energy. A clicker resting on the floor. We have none of the ones we've been talking about here. And so clearly it's not all of the above. And finally, if someone is standing in front of you, why can't you feel the gravitational force between you and the person? It is just too darn small. We went through the calculation last class period on the size of the force. And it's too small. So the answers you should have had were A blank CC. Yeah. Sure. or the Atlantic, some coastal conference. Is that what ACC is? I don't
How
know.
do you know though that you're not so used to it that you
Because I know that I cannot. Remember, we calculated that the force would be on the order of a millionth of a Newton, and I use the example of my lowest mass here. It's way lower than that. There's no way I can feel it.
Okay.
All right. I didn't get through projectile motion. I'm supposed to be doing fluids today. I've got my demonstration stuff for the very. What did I put? There's the box. Yeah. For the very end of this, probably won't get there, but we're going to try to get through this stuff. But I have to finish with the projectiles. So a projectile is something that's being projected through the air. So I take this ball, I throw it to Casey. Will you catch it if I throw it to Casey?
will I catch it?
Or at least try?
I will try.
Okay. Because I had a student, I threw it at her, and she just went, why did you throw the ball at me?
I might get
So that's why I asked beforehand. Okay, so I throw the ball to Casey. First of all, what direction am I going to throw the ball when I throw it to Casey?
Positive.
Okay, being more specific, because my question was too nebulous, clearly. Do I throw it in a direction directly at her forehead? Do I throw it below her forehead or above her forehead? Above. Why do I throw it above her forehead? Okay, it's going to fall down due to gravity. So I throw it, and there we go. And it would have hit her in the head if she hadn't caught it, right? Go ahead, throw it back. Okay, so when I threw that, the path it took, we call its trajectory. The trajectory is the path. And it was going through the air. Because I was throwing it initially above her, it went up, but then what happened to its upward motion? You all said it. Gravity makes it so it goes up, slows down, stops, and then starts coming back down. What about the horizontal motion? What was going on with its horizontal motion? Was it speeding up or slowing down in the horizontal direction? If we ignore air resistance, it was constant. If you include air resistance, yes, you're right. But the two directions, the vertical direction and the horizontal direction, we can treat the two directions completely independently. So I can calculate, okay, I threw it with this much horizontal velocity. She's that far away from me. It's going to take, and I can use my kinematic equations we talked about to calculate how long it's going to take to get her to her. And then based on that time, I say, okay, I'm also going to have this much vertical so it stays in the air that amount of time. So you do the two problems differently. And of course, I'm not going to do this, but let's say I wanted to throw it harder at her. Right? I'm not going to do it because, first of all, I get wild when I throw hard. And second of all, it's hard to catch, especially at this short distance. But if I threw it harder, how would I change the direction I was throwing? I would throw it lower, more directly, as Brittany said. Why? It's going to be less time to get there, so I don't need to go as high because I don't need as much time in the air. So, oh goodness. Here's what a trajectory looks like if you were to just throw a ball horizontally off a cliff. For fun, when I was at PUC, they have an airfield there, Parrot Field, virtual Parrot Field, I think. And they decided to have airplane Olympics. And they had different things they had to do. And the one that I liked was they painted a target on the runway. And the airplanes had to fly over at a specified height and drop a 5-pound bag of flour onto the target and try to hit the target. So the airplane's coming along, and it's just like this picture of throwing the ball. So let's say I'm playing that game. You guys see that crud sitting right there between Jocelyn and Hannah? So I want to drop my ball so it hits that crud. So I walk along at a constant speed. Where should I let go if I want the ball to hit that crud? Before. Why before it?
Because it's going to fall when you land on it.
Yeah.
If you drop it right then, it's just going to fall past it.
It's going forward, and I'm going to have to let go before. I let go before, but I let go too late because it cruised past it. Because it had a horizontal motion. Its vertical motion is exactly the same as if I just dropped it. But you have the horizontal, which stays constant. So let's try to do a better job. Still let go too late, right? And so that's what they're doing with the airplanes. They're flying over, and they're trying to determine, now, how much earlier before I get there do I need to let go? And of course, they could have gotten out their physics calculations and calculated at this height, it's going to take this long to get there. If I'm traveling this speed, it takes me, this much distance for that time. And they could have calculated where you should drop it, but then it still comes to, as you can see, even if you know where you're supposed to drop it, doing it at just the right time is still hard. So trajectories have to do with the acceleration of gravity in the vertical direction, making it so it goes up, comes back down. Here's a question that I think is on the next slide. Let's say I want to throw the ball as far as I can, and there's no air resistance, nothing like that to worry about. What angle should I throw it to get the maximum distance? 45. Now, the true answer is if it's going to land at the same height I throw it from, it's 45. Because, well, that gives you 70%, 71%, 70.7. 70.7% of your total speed is horizontal and 70.7% is vertical. Because when you have the hypotenuse and the two sides of the triangle, you guys know sine and cosine, that's how we break it up. And so it gives you the combination of as much speed in the horizontal and as much speed in the vertical as you can get. If you go a different angle, then like if you go flatter, your horizontal speed picks up, but your vertical speed drops. So it's not going to be in the air as long. If you go steeper, the vertical speed picks up, so you're going to be in the air longer, but the horizontal speed slows down, so you don't go as far in that time. So 45 degrees is the ideal angle if it starts and ends at the same height. Now let's say you're playing basketball. Unless you've got really mad hops for your jump shot, you're going to be releasing the ball below the rim. So if you're releasing below, what do you think your angle should be then? Say what? 180?
It's like flat.
Yeah, so if the hoop's over here, I'm going to throw it that way?
No, I mean, like, I totally calculated that wrong.
I 90 would be straight up, and that's not going to work for me.
Well.
What you actually want is a little bit steeper than 45 so that when it gets to the height of the hoop, it'll be at 45 degrees.
So 49.
It depends on where you are and whatnot, but yeah. So all we can say as a generic statement is a little bit steeper than 45 degrees. And when I was in college, back when I still tried to play basketball, I've always been horrible at the game. I could block shots in the end. I could go up and bang the ball off the rim. Doesn't help. But I read an article where physicists calculate, what is the optimal angle for shooting. And he found that for range as well as for accuracy, it was the same angle, the angle that makes it 45 degrees because of the height. So that's a cool application, I think, of physics in the sports world. How many people, now this is just showing what happens to the ball if you roll on a table, constant speed. If you drop it, it's speeding up. And when you throw the ball, it's doing both. What was the question I was going to ask? Oh, yes. How many people have heard the question about if there was no air and the earth was perfectly flat, is the earth perfectly flat? No. It's shaped roughly like a sphere. But if the earth was perfectly flat and there was no air resistance, if you pull your six-shooter out and fire a bullet, and at the same time you fire the bullet, you drop the bullet, which would hit the ground first? Has anybody heard that question? No? Well, what do you think the answer is? Neither is going to ever hit the ground. Good answer. Any other answers?
Probably the one you draw.
Okay, probably the one you dropped. According to physics, they'll hit the ground exactly the same time. But one of them's going really fast and one of them started at rest. So how do they hit the ground at the same time? The what? Well, we're assuming no air. So we don't have a terminal velocity issue if there's no air, because that's the only thing that would may have terminal velocity. If I shoot it horizontally, what's the vertical speed of the bullet when it comes out of the gun? How fast is it going up and down when I shoot horizontal?
Oh, that's gravity back there.
Well, the instant it comes out, it'll be 0. Then gravity will act on it and start to fall. And it will fall in the vertical direction due to gravity, so exactly the same as the bullet falls that starts at rest. Now, of course, I had to start this by saying, if there's no air, because air is going to make a fair amount of difference in reality. So we use this example in physics all the time, but we have to say, okay, so if there's no air, don't go home and try this. Of course, it's never going to work to go home and try it, because how would you ever find how long it takes for the bullet to hit the ground when it's hitting the ground very far away from you? The shape of the path the ball takes when I throw it to Casey is called a parabola. And so the shape looks like this. The vertical motion has y is equal to an equation like this. It has the highest exponent is times squared, and that's what makes it have the funny shape. The horizontal is just constant. X is equal to, well, let's put x0. So that's just a linear, so linear in one direction in time, square in the other direction. That's what gives you the parabola. Okay, now our first clicker question. When no air resistance acts on a fast-moving baseball, how quickly is it accelerating? Its acceleration is, oh, actually it doesn't say how quickly. It says, well, it has different answers. Okay, you answer the question.
Sorry.
And this is assuming that it's in free fall. You know, you don't have somebody that's in the process of throwing the ball, because that would, of course, change it. We have Maggie, Candace, Jocelyn, and Raquel. Okay, everyone's answered, and we have 3, 15, 0, 0. Oh, crud, that's a... When no air resistance acts on a fast-moving baseball, its acceleration is... And let's go to Tiffany.
All of the rest of the answers were short, and that one was longer, so I figured it was more of an explanation.
Went with size. Due to a combination of constant horizontal motion and accelerated downward motion. The acceleration is not going to be a result of constant motion. The acceleration is the rate at which its speed is changing. So what answer did you choose, Casey?
Oh, the yikes answer, which now it turns out is probably right.
That's correct.
Which is A.
A was the correct answer because the horizontal motion just doesn't matter if there's no air resistance. It's only the force of gravity. Net force is mass times acceleration. Force of gravity is mg. So mg equals ma. Cancel the m's. G is equal to A. So, like, the whole point of this was when I throw the ball, once it leaves my hand, it's in free fall, and free fall means Only the force of gravity is acting on it, and its entire acceleration is just going to be g downward. And so that's why you have to have faith in yourself and not, go with the majority. If the majority of people said, let's stop all immigration, is that okay? I am proud that Nebraska has like a huge population of immigrants. Now, part of the reason is because nobody wants to live in Nebraska, and so they bring immigrants here, they get assimilated in society, and then they go to a livable state. But Nebraska really is built on immigrants. And when we start saying we're not going to allow people who are suffering because of unrest to come because obviously we need to do some vetting and make sure we're not letting people come in who want to bomb us, but at the same time we need to welcome those who need us, right? I don't think that's a partisan principle. I think that's a Christian principle. That's how God would have us treat our fellow man. Okay, here is just talking about the range. One thing to notice here, remember I said the optimal angle, if it's going to start and end at the same height, is 45 degrees. As you veer away from 45 degrees, 30 and 60 are each 15 degrees away, and they end up at the same position. So what's the difference in throwing the ball with an angle of elevation, an angle above the horizon of 60 degrees compared to 30 degrees?
Speed.
These are actually thrown at the same speed. They're all at the same speed.
Oh, just kidding.
So what's going to be the difference? They get the same place. They have the same speed. They're acting under gravity. That's all I heard was gravity. If there was more explanation, I didn't hear it. Let's say I'm the quarterback, and I have a receiver that's running a post route, right? He's just blazing as fast as he can down the field, and I know where he's going. And there is some crazy defensive end bearing down me, and I have no time. How do I throw the ball in that situation? Higher. Why do I throw it higher? Because that's what this question was. Why do you throw it higher in that situation?
It takes longer to get the same spot.
It takes longer to get the same spot. So he's going really deep. I'm just going to rocket it high so it takes longer and he has time to run underneath it because I don't have time to wait and throw it on a rope to him.
So it takes less time.
So the flatter one takes less time. The higher one takes more time. But they'll get there at the same location, just a different time. And one thing that I haven't mentioned, something that's interesting, because the equations, if there's no air resistance, it's just, height has to do with time squared. The speed has to do with the height. You'll have exactly the same speed at some height going up as you have coming down. So if you start and end at the same height, you're going to have the same speed when it gets to the ground, regardless of the angle you threw it. It'll go slower as it gets higher and faster as it comes back down, which is just good to know. And that's what this is pointing out on this slide. At the same heights, you have the same speeds. Assuming there's no air resistance. What would happen if there's air resistance? Because that's kind of real, right? So it really happens. What is air resistance doing to the energy of the ball? It's taking it away. It's decreasing it. That energy is going into moving air molecules. And so if you have less energy, what does that mean about the speed? It goes slower because it lost energy due to air resistance. So if there's air resistance, it'll be slower on the way down than it was on the way up because you're losing energy. Now, getting back to satellite motion. Y'all heard of Kepler, Johannes Kepler? Yes. Johannes Kepler was famous because, he worked for Tycho Brahe. I don't have time to go through the long story. He examined Tycho's numbers and determined that we could explain the positions of planets if the planets did elliptical orbits about the sun, with the sun at one of the two focal points of an ellipse, which begs the question, what is an ellipse? Anybody know? It's an oval. So because the Earth curves, if I throw a ball on Earth, this picture's saying if this young lady throws the ball fast enough, gravity's going to make it change direction. But if she throws it fast enough, it can do a complete circle around and hit her in the back of the head. I would assume that the whole world was like Nebraska, flat. Yeah. If there's mountains, well, she has to be at the mountaintop where there's no other mountains in her path that are higher. But the fact is, let's get to, here's the picture for elliptical orbits. If you throw a ball a certain speed, and that speed can be calculated, we're not going to worry about how to calculate it, it will do a circular orbit. If you throw it faster, it has more energy, and so it's going to convert some of that energy into potential energy and go higher. But as we attribute to Newton, what goes up must come down. So if it goes higher, it doesn't stay up higher, it falls back down. And as it's going around, going higher and lower means it's stretching out a circle, making what we call an elliptical orbit. Now, one of the interesting things about these, if you do the math, which once again requires calculus, it's not something we do here, it turns out that it always will stay on that same path if there's no resistance, if there's no friction. In outer space, you know what there isn't? There isn't air. There's very, very, very rare molecules. So essentially it is true in outer space if there's no air resistance. And so they just stay on these nice elliptical orbits. So it's going the fastest down here because it has the least potential energy, which means it's converted as much energy as possible into kinetic. Out here, it's really far away. It's converted a lot of kinetic into potential. It's going the slowest. So you guys know what a comet is, right? You see them in the sky. Or you could watch a Walk to Remember and get a completely wrong idea of what a comet is. What?
15 years ago.
Yeah. Yeah, when it just came out, some students were going to watch it. And I said, hey, come up to my house. You know, I got 65-inch TV. You watched it. And man, that is the biggest drag of a movie. And it gets to the end, and this guy had made a homemade telescope. Aligning a homemade telescope is really, really tough. But somehow he did it. And then you see her come up, and you see her touch the telescope and move it. The telescope moves by any imperceptible amount. You're way off. Not looking close to what it was aimed at. And yet she looks through and she sees the comet, which means he must have had it aimed away from the comet, and then she moved it to the comet when she touched it. And then I swear it showed the comet like changing, okay? You don't see a comet change. It's a fuzzy blob out there with big clouds behind it, and you just see, ooh, big cloud. Okay, all of this said, I started busting up and the girls got really angry at me. But you know what? There is a worse movie than A Walk to Remember. You ready for it? The Notebook. Okay, so you go through this guy's like abusive to the girl. They end up getting married anyway. And then she's lost her mind. He reached to her. And then miraculously, they die the same night.
That was cute, though.
I started laughing uncontrollably. It took me 5 minutes to stop. And my wife was so angry, she banned me from watching chick flicks with her. So I totally won. It may have cost me like $20 to buy the Blu-ray movie and 2 hours of my life to suffer through it, but I don't have to watch it anymore. It's a win. Okay. A comet, when a comet comes by, how long is it visible? Not very long, a few months, right? And how long does it take? Second? Well, no. If it was seconds, then, you know, A Walk to Remember might have been realistic. Like, whoo, see, there it goes. They go slow enough that you will not see them move. You can sit there and look at it in your telescope for 2 hours, and you'll have no perceptible change in its position. But
so comets aren't just like
no,
those are asteroids.
Yeah. Shooting stars go quick.
Oh.
Which shooting stars are not stars at all. They're basically grains of sand coming into the atmosphere. Okay, but what's going on with these comets? The comet is something that orbits in a very, very elliptical orbit. So comets are doing paths around the sun, where here's the sun, and the comet is going, starts out here in either the Oort cloud or Kuiper belt, and we'll talk about this a little when we get to astronomy. something jostles it, and it comes in and goes like this. So where is it going to be going the fastest? Where?
Is that the Earth?
It's the sun, actually.
Or
When it's close to the sun. Why?
Most potential.
The potential energy.
It has lost almost all of its potential energy, has the lowest potential energy, which means it's converted that into kinetic energy, so it has the highest speed. Where's it going the slowest? Out here. So out here is slow, in here is fast. So you take something like Halley's Comet. There was a band, was it Bill Haley and the Comets or something like that? But the comet is named after Halley, so it's Halley's Comet. Halley's Comet comes by every 77 years. It last came by like when I was a freshman in college. All my friends went out to Lake Matthews to look at the comet. I was like, dude, that's at nighttime. I'm not going to be up at nighttime. You guys watch it. I was kind of stupid. Come again in 77 years. How long is it visible in the sky? Just a couple months. How can it only be visible in the sky for a couple months when it's 77 years before it returns? Because it was going really fast when it was close to the sun, which is when we see it. It goes really slow when it's out there. So we don't see it when it's going slow. When it gets very far away from the sun, it no longer is getting melted by the sun. It doesn't cause a cloud, and it just hangs out. You don't see it. Escape velocity. If I throw something fast enough, I should be able to give it enough kinetic energy to get away from the Earth. But on Earth, we can calculate, and if there was no air to contend with, I would have to throw this ball 11.2 kilometers per second. That's beyond my abilities. So I can't throw a ball to escape the Earth as shown in this figure. Now, if we went to the moon has a much smaller mass. And because it has a much smaller mass, it has a much smaller acceleration of gravity, about 1/6 on Earth. Which means the escape velocity is much slower on the moon. I still couldn't throw it fast enough to escape. But I like to pretend that if I was on the moon, well, we know on the Earth if I jump, I can stay in the air for, 1/10 of a second. Yeah, mad hops that I got at this age. But if I jump, gravity's going to bring me back down. On the moon, with 1/6 the gravity, if I jump, my downward acceleration is 1/6 as much. I'm going to be in the air a lot longer. I'm going to go a lot higher. Right? So on the moon, we would all have mad hops, yeah? Right? If we play basketball on the moon, we would have to move that rim way up, or we would just all run down and dunk.
How would we ever come back down, though? I don't understand.
It still has enough gravity that we could not generate the speed for escape with our legs.
So we would come down.
Yeah, we would come down.
Okay.
We might jump a long distance. I might jump from here to, Brittany.
It's like one hoop doesn't
But-
really seem worth it.
Okay, so escape velocity is the speed something has to have to escape. Now, have we sent things that have escaped from the Earth? Yes, we have. Do they leave the Earth with 11.2 kilometers per second? No. What they do, and this is really cool, you guys know, it ain't no rocket science. You have the Earth, and the Earth is spinning. And so they launch the rocket, and as soon as the rocket gets off the Earth, it starts flying on its side like that. And then they keep burning rockets. So they keep adding to the momentum, adding to the kinetic energy as the rockets burn. Why would they fly it on its backside so it's basically going the same direction the Earth is rotating? That's not going farther away from the Earth, so why do they do that? If you look at the half-done solution for your homework, you'll see I talked about it. Well, not about the space shuttle, but about this aspect. If I walk outside and I put my hand out and feel the air, in a general sense, how fast is that air going compared to the surface of the Earth? The same. It's generally moving with the Earth. Since the Earth is spinning, they rock it back on its side and go the same direction the Earth is spinning, so they're actually picking up additional energy from the spin of the Earth, because the air is being dragged along with the Earth. And so that means their actual speed is faster, and it helps them get up to escape velocity quicker because they're using the Earth's rotation to help them. And so they get out here, and then they will actually do things like, I want to get out to, let's say, Pluto, because the New Horizons spacecraft went by and viewed Pluto recently. Well, to get to Pluto in any amount of fast time, I'm going to really need to have a fast speed. And so I'm going to time it so Jupiter comes by. Here's Jupiter, which is, of course, much bigger than Earth. And time it so my satellite comes just behind Jupiter. Well, if it gets close to Jupiter, Jupiter has a gravitational pull, and it's going to pull it toward Jupiter. But if I'm behind it, then it's going to pull me forward. If I'm going fast enough, I don't actually hit Jupiter. Instead, I come off like this, and I pick up kinetic energy from what we call the slingshot effect because Jupiter pulled me in the direction it was moving. And so they call that the slingshot effect, and they use that to get higher and higher speeds for the orbiters. So now I actually didn't look at the textbook. I assume the textbook had the same mistake the slide had. This said that Pioneer 10, launched from Earth in 1972, was the first probe to escape the solar system. And that's patently false. The first, we have sent a space probe to escape the solar system, but it's actually Voyager 1. Voyager 1, which was launched in September 1977. It's gotten there, whereas Voyager 2, which was launched a few months before it, hasn't yet. Why? Because Voyager 1 used a better path to get that slingshot off of Jupiter. It got a higher speed quicker, and because of that higher speed, it's been able to travel farther. And so we have sent a probe outside of the solar system, where it no longer is considered bound to the solar system. They actually have a name for that. They call it the heliopause, because you have particles from the sun that are being blown off all the time. And you get to that heliopause, and all of a sudden, you get away from the particles being blown off from the sun. Do you have a question?
Yeah, I don't know if you know, but like, how does the cold not affect those?
Oh,
Those probes?
it's cold. I think they have, their source of energy that's providing heat, so that they don't, just freeze into a solid brick.
Right.
But it is cold, right? There's no question about that. There's also not much for them to lose energy to, right? If you have molecules that are hitting you coming very slow, you'll give them energy, they'll leave, and you'll lose a lot of energy quickly. But if you only have 3 molecules hit you a minute, they're not going to take off that much energy. And so you don't have much transfer of energy that way. You do have what we call radiation, but you don't have much loss that way either. So it's not a huge problem. There was a case where a person was accidentally put in a vacuum chamber, and they rescued him quickly enough, but he said the last thing he remembered before losing consciousness was the water boiling off of his tongue because of the low pressure. Just kind of bizarre.
It was hot?
No,
All right.
no, not hot. Boiling occurs when the partial pressure of the gas is higher than the partial pressure in the vapor around you. So if there's no vapor around you, every liquid boils. All right. I just have to point this out. How many people have watched the original Star Wars movie? With V'ger, right? That's the one with V'ger. And V'ger is supposed to be a Voyager module, but it's supposed to be Voyager 6, and there was no anything beyond Voyager 2.
That's
Yeah.
Star Trek.
Oh, did I say Wars instead of Trek? I get the two confused. It was really bad. I got a cousin who's totally into that stuff, Yeah, anyway, yes. It's Star Trek. It's the same episode where they use the classic line, Spock is dressed all funny, and Kirk says, I think you had too much LDS. Because LSD is not part of their culture. They're trying to remember what it is, and of course, LDS is Latter-day Saints. It's got a little too much Mormon. It makes it a funny joke. Yeah. Okay, moving on. When a projectile achieves escape speed from Earth, what happens? This is a tough question. Answer your best. I'm not going to call on somebody to answer this one. You want me calling? You ready?
Sure.
Okay. We have not even gotten to the fluids yet, which was the topic of the day. Eric, Carmen. Okay. Eric, Vanessa, and Raquel. Vanessa and Raquel. Raquel. Done. 2, 13, 1, 2. Okay. Escape velocity means that it's free from the Earth. It's not coming back. And so we can rule out the one that says returning to the Earth, which means we also can rule out all of the above. So those two I can rule out. But then we have the other two. Forever leaves Earth's gravitational field. Well, Earth's gravitational field, we learned from Newton that the gravitational field, well, the force of gravity was G m1 m2 over r squared. At what r is G m1 m2 over r squared 0?
Is it ever?
It isn't ever. You have to get infinitely far away before it is out. So it's actually impossible to leave the Earth's gravitational field. Right? We are in the gravitational field of every object. Really, really weak for most of them, except for the Earth, but we're in their gravitational field. So that leaves us the one that the majority of people answered. It outruns the influence of the Earth's gravity. That is, you get far enough away that the influence of Earth's gravity is meaningless to you. And so it's not coming back because it's just got this meaningless tug that's too small to register. But it was a tough question, right? For test questions, I want to try to make it so it's a little more clear. Okay. 2 minutes to cover chapter 5. Think we can do it? Yes, we give it the old college try because we're in college here. No, we're not going to try it. I'm just going to talk about density and end. So density. Density, I know when I was a child, people said that Richard, he's dense. And that was because they were mean. Density is, this says lightness or heaviness of materials. If you don't have the rest of that statement, it's false. Of the same size. Density is a measurement of the mass divided by volume. So I can take two things that are the same size. Let's say this ball and one of these balls. They're all about the same size. And so if I take these and I say, okay, they're the same size, but I have a hard time. But this ball is clearly lighter than this ball, then the one that's the same size but heavier is more dense. Because the density is the mass per volume. And of course, how heavy it is proportional mass. Now here's something cool just because I got the math. These two balls, they look the same, right? How do they feel? Of course they're not. Otherwise, why would I use this?
Well,
This one's heavier.
Okay, he said this one's heavier. It might be. They're supposed to be the same, but it does feel like you're right on that. You drop them, what's going to happen?
They should hit at the same time.
They should hit at the same time. Good call, Brittany.
what? That's not science.
Sure it is. What's the difference between these two?
One's denser.
It is true. The more I think about it, the more I think he's right. This one is a little more dense. But the difference is if you squeeze them, this one here, I squeeze it, and when I let go, it stays with my fingers. This one here, when I squeeze it and let go, it doesn't rebound quickly. It's more spongy. If it's more spongy, when it hits the table and doesn't rebound quickly, it doesn't give energy back. It just is slowly coming out. This one that rebounds quickly, it bounces nicely. And so we talked about the coefficient of restitution, how much energy it returns. One of these has a fairly high coefficient of restitution, right? Return at least 90% of the energy. The other one had a coefficient of restitution of less than 5%. Okay, we're out of time. Have an excellent Sabbath.